Good day, everyone. Today we're going to focus on our lesson 2, which is all about geometric sequence. For our objective for today, we're going to differentiate geometric sequence to arithmetic sequence, distinguish the geometric mean, the end term, and the sum of the given terms, finite and infinite geometric sequence. At the same time, we're going to solve problems involving geometric sequence and show and demonstrate the flow of geometric sequence. Let's get started. Okay, to start with, we know in terms of having a geometric sequence, one of the criteria it is there should have this what we call common ratio. And when we say ratio, it is in a form of a fraction of a over b, wherein the a here considered the a sub n, and the b here is considered the a sub n minus 1 or the previous term. So we're just going to divide the term, a given term to the previous term for us to get the ratio of the given sequence. And in order to consider it as a geometric sequence, one thing is it should be common. Okay, there should be a common ratio between those terms that we have. Let us have an example. So I will give you 1 minute for you to identify what might be the common ratio of this sequence. Okay, so to answer this, simply what we are going to do is we're going to divide the term to the previous term. Okay, so here we have now 4 divided by 2, the answer is 2. And when we have now the term 8 divided by 4, we have 8 divided by 4, the answer is also 2. Same goes with 16 divided by 8, the answer is equivalent also to 2. Same goes with 32 divided by 16. The answer is 32 divided by 16. The answer is also 2. As you can see here, there will be a common ratio between those different terms. Therefore, this one is considered as geometric sequence. And for us to find the next 3 terms, what we are going to do is we're just going to multiply the given term to the common ratio that we have. Same goes with here. We have now 32 times the common ratio, which is 2. We have now 64. 64 times 2. We have now 128. 128 times 2. We have now 256. So as we can see here, the next 3 term will be 64, 128, and 256. The next thing that we are going to look for is we're going to find the 15th term of the given sequence. And I'll give you 1 minute for you to identify those given in this sequence for us to look for the 15th term. Based on the given formula that we have. Okay, so let us have the details of this formula. First, we also have this a sub n, that is the value of the missing term that we are trying to find out. So here we are trying to find out the a sub 15. The next thing that we are going to look for will be the a sub 1. A sub 1 is considered the first term of the given sequence. And in here, the first term is 2. Next, we are going to look for our ratio. Okay, the common ratio of this kind of sequence is also 2. And we also have the n. N is considered the order of the missing term or the term position. And we are trying to look for the 50th term or the 15th term rather. Therefore, our n is equivalent to 15 minus 1. And let us now try to simplify this. Now, I'll give you 1 minute for you to simplify this equation. Okay, so let us try to look for the 15th term by means of simplifying this. We have a sub 15 that is equal to 2 times 2 raised to 15 minus 1. So here, what we are going to do, first, let's take a look with the exponent 15 minus 1. The answer is 14. So we have now 2 raised to 14 times 2. So we have now 2 raised to 14 that is equivalent to 16,384. Then we're going to multiply it by 2. We have now 32,768. And that would be our a sub 50. Now, let us take a look for the nth term or what we call the recursive formula or the general term of this sequence. Now, I'll give you 1 minute for you to look for the variables or the given for this kind of sequence. Okay, so let us take a look on those variables that we are looking for. We have the a sub n, which is the missing term. And since we are looking for the n term, we still have the a sub n. The next thing that we are looking for will be the a sub 1 or the first term of the given sequence. And in here, we have 2. For the common ratio, as we all know, the common ratio of this kind of sequence is 2. Now this time, if you're looking for the n, simply, since it is a general term for this kind of sequence, we're looking for just the n, minus 1. And let us now try to simplify. A sub n is equal to 2 times 2 raised to n minus 1. Now, I'll give you 1 minute for you to simplify this equation. Okay, so let us now simplify this. Okay, so let me rewrite first. A sub n is equal to 2 times 2 raised to n minus 1. So to simplify this, we're going to extract 2 raised to n minus 1. So it will become now 2n times 2 raised to negative 1, since it is part of the given law of exponent. Based on the law of exponent, 2 raised to n times 2 raised to negative 1 is equivalent to 2 raised to n minus 1. Okay? So, next thing that we are going to do, also based on the law of exponent, the 2 raised to negative 1, or the negative exponent, can be changed into a given fraction, wherein if we're going to change 2 raised to negative 1 into fraction, it will become, first, we are going to get the reciprocal of the base, which is 1 half. And then afterwards, the given exponent negative 1 will become now positive. So we have now 1 over 2 raised to positive 1. Okay? The next thing is we're going to bring down 2 raised to n and 2. And after that, we're going to simplify this. Those with numerical value or the constant will be multiplied. 2 times 1 half, we all know that it is equivalent to 1. Times 2 raised to n, we have now 2 raised to n. So the nth term or the recursive formula, or what we call the general term of the sequence, will be a sub n is equal to 2 raised to n. Now, let us try to find the 5 geometric mean between 5 and 3,645. I'll give you 1 minute for you to look for the 5 geometric mean of this sequence. Okay, so in this part, if you're going to look for the geometric mean of these two terms that we have, 5 and 3,645, specifically 5 geometric mean, the first thing that we need to do is we need to look for the R, or what we call the common ratio. Okay, so we are going to look for the R. So let us first rewrite what we have now on the sequence. So we have 5 as the first term, and we have 5 geometric mean that we are going to include in the given sequence, and we have the last term that we have, which is 3,645. Given those things, what we are going to do is we have now the a sub n. that is equivalent to 3,645. The first term, that is 5. And we have now the n, which is considered the order of the last number. So here, if we're going to look for from 5 up to 3,645, the 3,645 will be the seventh term. So if you're going to count for that, 1, 2, 3, 4, 5, 6, and the seventh term. First, second, third, fourth, fifth, sixth, and the seventh term. Now, our n will be 7 since 3,645 is the seventh term of this sequence. And using the formula a while ago, which is a sub n is equal to a sub 1 times r raised to n minus 1, we can now find the common ratio. We have a sub n, let us substitute the values. We have a sub n, which is 3,645, and we have a sub 1, which is 5. We are looking for the r, and the n is equivalent to 7 minus 1. Let us simplify. We have now 7 minus 1, that is equivalent to 6. So we have r raised to 6 times 5 is equal to 3,645. Now, what we are going to do is we're going to divide both sides by 5 for us to remove the numerical coefficient that attached to our variable r. So here, we're going to cancel out 5. And now we have r raised to 6, that is equivalent to 3,645 divided by 5. And the answer will be 729. Now we're going to extract the sixth root of 729. So to do that, we're going to get the sixth root of both sides of the given equation. So we have now sixth root of r raised to 6, we have r. And the sixth root of 729, we have 3. So the common ratio on this kind of sequence will be equal to 3. And for us to find the 5 geometric mean, simply we're just about to multiply the first term or the term to the given common ratio. So we have 5 times 3, we have 15. Times 3, we have 45. Times 3, we have 135. Times 3, we have 405. Times 3, we have 1,215. And times 3, we have 3,645. And as you can see here, we could get the given 5 geometric mean, which is 15, 45, 135, 405, and 1,250. Okay, those are considered the 5 geometric mean of this sequence. Now, let's take a look on how are we going to lead ourselves with the sum of the finite geometric series and also the infinite geometric series. So let us now first differentiate the two. When we are trying to solve for the finite geometric series, remember that the common ratio that we have should always be greater than 1 or it is less than -1. And when we are dealing with infinite geometric series, the ratio of the given sequence should always be less than 1 but greater than -1. Okay? So let us try to look for the given generated sequence knowing that the a sub 1 is 10 and we have this given sample of common ratio. So I'll give you 1 minute for you to generate the sequence based on the first one. We have 0.5 as the common ratio and the other one is 2 as the common ratio. What might be the given sequence. Okay, so let us try to find out. We have here our first term, which is 10. And to look for the other term, what we are going to do is we're going to multiply the common ratio to the given term. So we have 10 times 0.5, we have 5. Times 0.5, we have now 2.5. And 2.5 times 0.5, we have 1.25. Times 0.5, we have now 0.625, and so on. So that would be the generated sequence when we have the common ratio 0.5 or 1 half. And while in the given common ratio, which is 2, we could get from the first term, which is 10, multiplied to 2, we have 20. Multiplied to 2, we have 40. 40 times 2, we have 80. And 80 times 2, we have 160. And so on. And as you observe, if we have a given common ratio that is less than 1, the generated sequence is decreasing. And if we have the common ratio that is greater than 1, the generated sequence is increasing. Okay? That is how are we going to identify the flow of the given sequence based on its common ratio. Now let's take a look if we are looking for our common ratio when we have negative 2 and we have the common ratio when we have negative 0.5. I'll give you 1 minute for you to generate this sequence. Okay, to generate the sequence started from the first term, which is 10. We're going to multiply to the common ratio, we have negative 2. 10 times negative 2, we have negative 20. Negative 20 times negative 2, we have positive 40. Positive 40 times negative 2, we have negative 80. And negative 80 times negative 2, we have positive 160, and so on. And if we have the common ratio that is negative 0.5, we have the sequence starting from 10. 10 times 0 times negative 0.5, we have negative 5. Negative 5 times negative 0.5, we have now to positive 2.5. And positive 2.5 times negative 0.5, we have now 2.5 times negative 0.5, we have negative 1.25. And from negative 1.25 multiplied to negative 0.5, the answer is positive 0.25. 625, and so on. So as you observe here, when we have the given ratio that is in negative, the generated sequence is being alternately increasing and decreasing in number. So as you can see, we have here 10 become negative 20, increased by positive 40, decreased by negative 80 again, and increased by 160. That is when our common ratio is negative. Now let us proceed on how are we going to deal with the finite geometric series. Again, in dealing with finite geometric series, the common ratio should always be greater than 1 and less than negative 1. And we have these two formula for us to look for the finite geometric series. The first formula is used when there is no a sub n, okay? Or the a sub n is unknown. And the second formula that we have is being used when the a sub n or the last number is known or given. Let us try. Find the sum of the first 15 terms given that the sequence is 2, 4, 8, 16, 32. Using the first formula that we have, that the a sub n or the last number is not given, and we try to find out the sum of the first 15 terms. Okay, let us now try to find the sum of the first 15 terms. First, we're going to look for those variables given. We have a sub 1. Here we have the a sub 1, which is 2, the common ratio, which is 2, and the n, which is 15, since we're looking for the sum of the first 15 terms of the given sequence. Now, let us substitute the value. We have a sub 1, which is 2, times 1 minus the r or the common ratio, which is 2, raised to n, which is the order of the term, which is 15, the order of the last term, all over 1 minus the common ratio, which is 2. Let us simplify. 2 raised to 15, we have now equal to 32,768. Okay, so we have now 1 minus 32,768 times 2 all over 1 minus 2. The next thing, we have now 1 minus 32,768, which is equivalent to negative 32,767 times 2, and we have 1 minus 2, which is equivalent to negative 1. The next thing, we're going to multiply 2 times negative 32,767. The answer is negative 65,534 divided by negative 1. And if you're going to divide that, negative divided by negative, we have now positive. So the answer will become positive 65,534 as the sum of the first 15 terms of the given sequence 2, 4, 8, 16, 32, and so on. Now let us try to use the other formula wherein we are looking for also the a sub n or the last number. I'll give you 1 minute for you to finish it. Okay, so let us now try to find the sum of the first 15 terms of this sequence. And by this, first thing that we are going to do is we need to look for the a sub n. And for us to look for the a sub n, we're going to use the formula a sub 1 times dr raised to n minus 1. Okay, given that we have here a sub 1, which is 2, r, which is 2, and the n, which is 15. We're going to look for the a sub n, or the last number. Okay, let us substitute the value. We have a sub 1, which is 2, times the r, which is 2, raised to n, which is 15, minus 1. Okay, so we have now 15 minus 1, we have 14. So we have 2 raised to 14 times 2. Then after that, 2 raised to 14, we have 16,384 times 2, we have now equal to 32,768. After we find out the last number of the given sequence that we are going to add, let us use the formula for the geometric series. So we have now the sum of the geometric sequence is equal to a sub 1 minus the common ratio times the a sub n all over 1 minus r. So we have a sub 1, which is equivalent to 2, minus the common ratio, which is 2, times the last number, which is 32,768, all over 1 minus r, which is the common ratio, which is 2, and let us simplify. We have now 2 times 32,768, which is equivalent to 65,536. So we have now 2 minus 65,536 all over 1 minus 2, we have negative 1. Okay, to simplify, we have now 2 minus 65,536, that is equivalent to negative 65,534 all over negative 1. And to simplify, negative divided by negative, we have positive. So the final answer will also be 65,534. Either of the two formula, get the correct answer. Okay? We just need to look for which one is given. The first formula will be used if the a sub n, or the last number, is not given, and the second formula will be used if the a sub n is given, or the last number is given. Now let us proceed with the last one, which is about the infinite geometric series. We know when we have the infinite geometric series, the common ratio should be less than 1 or greater than negative 1. Okay? So to look for, this is our formula. The infinite geometric series is equivalent to a sub 1 all over 1 minus r. Okay, let's take a look for the infinite geometric series of this sequence: 32, 16, 8, 4, 2, and so on. I'll give you 1 minute for us to look, for you to look for our infinite geometric series. Okay, now let us take a look on infinite geometric series. And for us to find out the infinite geometric series, we are going to use this formula. Okay, the thing that we need to do or to know is the a sub 1. And in here, the first term is 32. And we need to look for the common ratio. And the common ratio of this kind of sequence we have is 0.5. Given that we have the first term is 32 and the common ratio which is 0.5, we could get the infinite geometric series of this sequence. Okay, let's take a look on that. Let us substitute the value. We have a sub 1 which is 32 all over 1 minus 0.5. And now, we have 1 minus 0.5. The answer is 0.5. So we have 32 divided by 0.5. 32 divided by 0.5, the answer is 64. And that would be the infinite geometric series of the given sequence 32, 16, 18, 4, 2, and so on. It means that if you're going to add all the numbers infinitely, starting from 32, 16, 8, 4, 2, and so on, we could get, or the answer will be near to 64. And it will be constant to 64 only. That is the infinite geometric series. In this lesson, we are done in distinguishing the geometric sequence by means of the common ratio that we have. We also try to find out the formula in finding the nth term of the given sequence. We also try to find the difference between finite and infinite geometric series. And also, we find out the different formula to find the finite geometric series when we have the a sub n that is unknown and the a sub n is given. And last one, we tried to find out also the formula in finding the infinite geometric series. That would be our topic for today, geometric sequence. That would be all. Thank you and see you on the next lesson.